Hi, this is Ronald, and welcome to Learn. Before we get started, I just wanted to draw your attention to the accompanying blog entry, link in the description, that's meant to act as a primer or glossary of sorts so that you guys can have a handy little reference. Not everyone has a background in biochemistry or medicine, and many of the terms are themselves interesting enough to write a little on. Check it out if you'd like a little bit more depth or nuance. The novel coronavirus, SARS-CoV-2, COVID-19, the Rona. Whatever you've settled into calling it, this one little virus has, in just the last few months, changed our society profoundly from top to bottom. But what is it? Is it a bioweapon? Some lab-grown Frankenstein given to us by science? Or is it the result of plain bad luck? What do we know, and what don't we know? What can we do to prevent its spread? Is it even important to prevent its spread in the first place? Are there any treatments, and how good are they? Questions like these will come to the fore as we all stumble through the dark to face this new challenge. Today, we're going to go through these basic questions and see if we can get a clear working idea of what this virus is all about. The novel coronavirus, SARS-CoV-2, discovered in 2019, causes a disease dubbed COVID-19, which literally stands for Coronavirus Disease 2019. So to start off, let's just be perfectly clear on where the name comes from. It's not the 19th coronavirus or anything like that. It's just that it was a coronavirus discovered in 2019. Now, it's by no means the first coronavirus to have ever been discovered, nor is it the only coronavirus to plague society in the recent past. Human coronavirus infections more broadly were first documented in the 1960s, starting with the strain B814, a common cold virus taken from a tracheal specimen. And around the same time, another strain called 229E. Interesting note on the microbiological methods of the time, these were ether sensitive, and scientists correctly inferred that the viruses had lipid coats. The same group that originally discovered B814 would go on to observe a variety of morphologically similar viruses in humans and animals, ultimately leading to the formal recognition of Coronaviridae as a distinct viral genus. More recently, we had the SARS epidemic of 2002 and 2003. That one was transmitted by Himalayan palm civets, which were thought to be an intermediary host for severe acute respiratory syndrome coronavirus, while bats were thought to be the natural reservoir. Now, this one came out of China, just like COVID-19, and blasted half the world before up and leaving. The thing about SARS is that it really earned the name severe acute respiratory distress syndrome. Typically, when you got SARS-CoV, you got pretty sick, and a lot of the time you ended up going and getting help. Although it should be noted that SARS also did have asymptomatic infection, is up to 7.5% in healthcare workers by some estimates, and less than the general population by other estimates. Of note, it used ACE2, a membrane-associated enzyme meant to catalyze the conversion of angiotensin 1 to angiotensin 2 as its receptor for entering human cells. So this is how SARS got into human cells. As we'll see in a minute, the reason I'm pointing that out is because COVID-19 also uses this same enzyme. Even more recently, MERS-CoV, or Middle Eastern Respiratory Syndrome coronavirus, hit the Arabian Peninsula in 2012. This apparently came from dromedary camels. You really couldn't walk this one off. Its mortality rate was just about 30%, so this one was a very deadly one. There's some asymptomatic mild disease cases that drove an infection and transmission, but usually, if you got MERS, you got sick. Of note, regions affected by MERS included not just the Arabian Peninsula, but South Korea. Why is that important? During today's novel coronavirus outbreak, most of us have kind of noticed that China and South Korea, some of these early places that got hit, were able to get their coronavirus cases under control faster than other countries. Part of that is related to the fact that they've already experienced zoonotic coronavirus epidemics in the recent past, and they kind of already knew what to do this time around. Realistically, we all kind of knew, but they were experientially, involved. And we'll circle back to that thought near the end of this. Another interesting side note, the New Haven coronavirus, or HCoV-NH, discovered around 2005, was associated with a potentially virally induced Kawasaki disease type syndrome. And we'll come back to that in a moment. So getting back to SARS-CoV-2, we'll note that it's an enveloped, positive sense, single-stranded mRNA beta coronavirus with helically symmetrical nucleocapsid measuring 125 nanometers across versus the 100 nanometers for influenza. So what does that mean? Well, once again, make sure to hit up my blog, link in the description for a little primer for more and more detail. But for now, notice that this means that it is an RNA virus. So that's the type of genetic material. It's not DNA. What's the difference between RNA and DNA? It's a single oxygen group. It's a relatively small difference, but it makes a huge biochemical difference. It behaves very differently from DNA. And it's a single-stranded virus, so it's one strand of RNA. And there's a lipid envelope around it, which typically that's used to harbor some proteins that it uses to actually get into the cell, and some structural proteins as well. Other proteins that actually surround the genetic material are symmetric around a central axis. So the nucleocapsid is helically symmetric. So in other words, the RNA is kind of twisting inside, and it's more or less kind of like a cylinder made of protein that's around the genetic material that protects it. And it's symmetric. If you draw a line straight down, that helix is symmetric in that sense. You've probably seen this particular type of viral nucleocapsid somewhere in like popular culture. For whatever reason, it's used often. More on that in the blog entry. There are alpha, beta, gamma, and delta coronaviruses. The majority of the significant ones that cause disease in humans are the beta coronavirus, and that does include SARS, MERS, the big ones that hit humans, typically betas. Deltas and gammas typically affect more like birds. Alphas and betas generally can affect humans and other animals. And SARS-CoV-2 shares a lot of features with these other coronaviruses. Its life cycle is lytic, meaning it cuts up the cell that it produces, it upon completing its replication. So it kind of makes a bunch more of itself and then tears out of the cell, and the cell dies. It buds from the endoplasmic reticulum into the cytoplasmic vesicles. So that kind of just means that the cell is producing it in a certain place, and then it gives it vesicles or kind of lipid kind of envelopes, almost like, that the cell makes, and it buds off of the endoplasmic reticulum. So the endoplasmic reticulum will have some lipid, and then a little bit of that lipid kind of just starts to bud off, and it surrounds the forming virus. Like SARS-CoV-2 before it, it's thought to enter cells via ACE2, like I had mentioned. And like the New Haven coronavirus before it, it's associated with a virally induced Kawasaki's disease. Coronavirus, the novel coronavirus, has an incubation period of as long as 14 days with a median of about 4 to 5 days. We'll look at an interesting application of this at the end as well. SARS-CoV-2 is thought to be genetically distinct from its predecessors, despite its remarkable homology in some sequences with the original SARS-CoV virus. It's thought to be more closely linked to two bat coronaviruses, so bat SL-CoV-ZC45 and bat SL-CoV-ZXC21, suggesting that the bats may be the original species. This may or may not be true. So where exactly did COVID-19 come from? That's the real controversy. We initially thought that it all started in a wet market in Wuhan, China, where bat stuff was circulating. They were in close contact with the bodily fluids of bats, and there were some bat-incorporated kind of dishes. Then the Chinese Center for Disease Control found that the wet market couldn't have been the origin, but rather the site was a super spreader event that followed dozens of previous cases throughout Wuhan. So for the moment, we don't actually know where it came from as of July 2020. The appropriateness of China's response to the initial outbreak has been questioned, but we're not going to touch that yet. The situation regarding the novel coronavirus's origins are a developing story and something I'd rather wait off to talk about until the dust is settled and we have a final story. It's a little early to say these things. There's a lot of speculation, though. For the moment, it seems to me that we have relatively little reason to believe this is an intentionally designed bioweapon or something like that, because frankly, the technology largely isn't there yet. Previous plagues killed way more than this one, and ultimately, Mother Nature is still leagues ahead of us in terms of making things that could kill us. For this particular virus, studies suggest that its ability to bind ACE2 is rather suboptimal compared to SARS-CoV, and genomic investigations suggest that no known method of reverse genetic modification for coronaviruses was involved in SARS-CoV-2. So this is kind of an interesting point here. If you were going to make a bioweapon out of the SARS virus, you'd probably make it so that it can actually bind ACE2. The thing that it uses to get into cells, you probably want it to bind ACE2. Now, if you were going to study it in a bioweapons lab, this is actually something that you might do intentionally. If it's less good at getting into cells, it should be less transmissible. So this is one thing that you can kind of program into the genetics of your virus to try and make it less likely to be a pandemic if it were to get out of the lab. Furthermore, there are some, they're called reverse genetic methods that you can use to modify coronaviruses. And this is kind of a standardized thing that they do use in labs, that we can kind of look at their genetic sequence and tell that these have been used. This doesn't seem to be the case for SARS-CoV-2. Now, despite this, I do think we probably have more to fear from random acts of mutation and natural selection than we do from communist scientists and secret labs. But we can't exclude the possibility of unintended consequences. If a virus escapes the lab, it takes everything with it. It takes its modifications, it takes whatever they've done with it. And it can disseminate those modifications to similar viruses by recombination. So interesting thing about this virus is that it has some genetic code that is very rarely seen in nature, but is potentially expected for lab viruses, which alerts some suspicion, especially because zoonotic infections have to accomplish both trans-species jumps and intraspecies jumps. So you see sometimes these stories about people who get maybe covered in rat dung for whatever reason. They go into a cave or something, they're unprepared. They get some kind of really virulent disease that nobody can identify, and then they die of it, but you don't see other cases of it. So that's potentially an example of something that makes a trans-species jump, but doesn't really do very well at making intraspecies jumps. You actually see that from time to time. There are news stories about these things, and that's basically what's happening, right? There's two different processes, and it has to do both. What's interesting is that COVID-19 is really, really good at this. It can not only jump from bats or pangolins or whatever the original reservoir or intermediate host ends up being, but also from humans to cats and humans to dogs. And it's not just house pets, right? It's lions, tigers, ferrets, minks. We could give COVID to all of these types of animals. COVID is really good at jumping species. And it seems like it's particularly good at jumping to dogs. So it's honestly really impressive in that regard. On top of that, a local Wuhan lab has been known to publish research about what's called gain of function mutations. And this was done explicitly on coronaviruses. If there were any type of research that could potentially give us a dangerous result that could potentially lead to this current pandemic, it's exactly this type of research. So until we have more data about what's going on with this modern coronaviruses, the issue could honestly go either way. It could go either way. I can kind of see why people would think there was some human intervention here. But somehow I think if there was intervention, it was entirely accidental, or at least not done with the intention to kill. We'll see. Oh man. This is the realm that I think public officials have done the worst job of communicating so far. So often I hear them get asked a question. In my head, I'm thinking, the right answer here is, I don't know. And neither does anybody else. But time and time again, what ends up being said is some long, rambling version of this that gives the vague impression of an actual answer. When it comes right down to it, It's impossible to have a clear idea of what questions need answering if we don't know what questions to ask or if we think or assume that we know things that we don't. Of course, you can't necessarily blame public health officials for their approach, as it's kind of their job to provide answers. The public wants answers, they gotta say something. So here's some stuff we do know. COVID is a pandemic. It's on every continent except Antarctica. It has greater than 10% mortality rate in people over 80 and almost 8 to 9% in people in their 70s. A study published in The Lancet suggests an 80% fatality rate for people over 80 that got put on ventilators. It very rarely causes severe disease in the young and has been associated with a deadly vasculitis, a virally induced Kawasaki's disease in children. In some cases, adults are getting this too. Obesity is a major risk factor for worse disease, and we're seeing that in the hospital big time. Males and African Americans seem to be hospitalized more often. It can be aerosolized for up to 15 minutes simply by loud talking, screaming, singing, but is mainly thought to be transmitted through respiratory droplets. Fomite transmission is thought to be very difficult and may ultimately be not a thing. We'll see. Apparently, stool shedding is definitely a thing, so wash those hands, people. Viral shedding continues after recovery. The vast majority of cases are asymptomatic or mildly symptomatic, especially in the young. This has been pointed out as a potential driver for its dramatic spread. Your cats and your dogs can get it from you. We don't think you can get it from them, though. We know that physical distancing measures and hygiene measures work, and we'll talk about why later on in this video and why they're important, especially if you're interested in herd immunity. Here's some stuff we do not know. We don't know if it's seasonal. We don't know the true case fatality rate. We don't know the exact specifics of transmission and all the different possible animal vectors involved. We don't really understand why it can apparently infect almost every organ system and cause such a variety of disease. It may well just be related to the ubiquity or distribution of the ACE2 receptor. It's in a lot of different places. We'll mention that in a second. We don't know how effective homemade masks are really going to be. We don't know how long immunity lasts. This could be an issue as an immune period of just a few weeks or a few months would preclude us from being able to achieve effective herd immunity. We don't know what the effects on fetuses will be, but I'm willing to bet there will be at least low birth weight. Usually when viruses, start to get involved and they start infecting blood vessels and placenta, stuff like that, you're going to see some decreased blood flow to the fetus, and you see low birth weight as a symptom of viral infection for a lot of different viruses and a lot of different conditions generally. It's one of the things that goes first, it seems like. But that's conjecture. That is my personal conjecture. We don't know what the long-term consequences of the infection might be generally. One thing you can look up for that is subacute sclerosing panencephalitis caused by hypermutated measles, or refer to the blog entry. You can look that up or refer to the blog entry. I have some more details on it there. We don't know if or when it will go away, and we have no idea what the appropriate way or what appropriate threshold to use for reopening the economy. Our governors and lawmakers are not gods, and they have to do the best they can with what they've got. We don't know when we'll get a vaccine as of the making of this video, July 2020. So the most common symptoms of COVID-19 are fever, cough, shortness of breath, in that order. You've probably heard that bit before, but what's really interesting about COVID is that it really can cause major illness in multiple organ systems outside the traditional viral pneumonia in the lungs. Loss of taste, loss of smell are recognized as early manifestations. COVID conjunctivitis is a well-documented entity at this point, as is COVID myocarditis, which is inflammation of the muscly part of the heart. COVID gastroenteritis is also quite common. In fact, at least some gastrointestinal manifestation is thought to be present in something like 40+% of cases. Symptoms like abdominal pain and diarrhea may even be the only ones you get. And remember, this is not even counting secondary bacterial or fungal infections that a disease like this can leave you susceptible to afterwards. More on that in the end. That is kind of important in the near future. The most common manifestation by far for COVID is viral pneumonia, like I was saying. If you go in and get a chest x-ray during an evaluation for COVID, your doctors are looking for evidence of what's called a viral pneumonia on your imaging studies. This is usually seen as a hazy lightening over your lungs on your x-ray. We call these ground glass opacities. CT, or computed tomography, sometimes known as a CAT scan, has been found to be 97% sensitive for COVID pneumonia. This is documented in a study by I et al. And while this is definitely used to support a diagnosis of COVID, it's really more useful as a kind of a positive, thing. You can use a positive study to support your diagnosis, but a negative imaging study typically won't exclude it if it's an X-ray. Highly sensitive CT is a pretty solid rule-out study for COVID pneumonia, but it really only rules out the COVID pneumonia. Like I said, you can have COVID without any lung findings. You can have just the gastroenteritis. This has all been taken into account with a detailed history and physical examination, including vital sign measurements. Importantly, this is going to include taking your temperature, your blood oxygen saturation, and measure how fast you're breathing. COVID is known for causing some high fevers, and when it gives you trouble breathing, it's not uncommon for you to start breathing faster. One important thing to consider is your oxygen saturation. The hemoglobin in your blood is typically going to be well saturated with oxygen. Most of the oxygen carried in your blood is on the hemoglobin protein. Not so much of it is dissolved into the blood itself. It's carried in the protein to compensate for the fact that your blood can only hold so much oxygen. So typically your O2 sat, when we measure it, should be in the high 90s, high to mid 90s if you got normal lungs, which, any healthy individual should see that kind of saturation. In people with bad pneumonia, that saturation can go low, below 92, which is when we typically start giving you oxygen. So this is really the big important COVID population, right? There's the asymptomatics. There's the people who are bad enough to go to the hospital and get oxygen. Then there's the ones that get much, much worse. And we'll talk about that spectrum in a second as well. So how do we manage those patients? Well, like I said, initially we'll give them a nasal cannula. This is just a tube that blows air into your nose at a certain rate, and we can pick that rate. Normal nasal cannula will give you up to 6 liters of air per minute. You can go to high flow nasal cannula and go all the way up to 15 liters per minute. And on top of that, you can go to a mask. So once the nasal cannula gives you a certain amount of oxygen, you can go to the mask and go even higher. And then once you pass that, once you ascend this ladder of oxygenation, you can go to things like Airvo or heated high flow nasal cannula. This can give you up to 60 liters per minute of air in your lungs at one time. That'll clear out your sinuses, I promise you. If you've ever used the Airvo before, or the high flow heated nasal cannula, it'll clear out your sinuses. Let me tell you that. BiPAP is another option, but that's really used more for people who are having trouble blowing off CO2 and ventilating themselves. Once you fail these more heavy-duty modalities, the BiPAP or the high-flow heated nasal cannula, then you start looking at ventilators and ventilator strategies and stuff like that. One peculiar feature of COVID is something that we call apathetic hypoxemia or happy hypoxia, a state in which people with very low oxygen saturation, a state in which people typically feel lightheaded or very short of breath or symptomatic to some extent. They'd be uncomfortable. They typically report feeling totally fine. And another thing that we've been seeing in the hospital in patients is that they seem to have prolonged periods where, oh no, I got it. They have prolonged periods where they need high levels of oxygen. And then suddenly one day they get way better and we send them home. Of course, there's also cases that are stable for a long time and then out of nowhere, they'll get a pulmonary embolism and things just deteriorate from there. More on that in a minute. It's not uncommon for COVID pneumonia to escalate into something that looks like what we call ARDS, or acute respiratory distress syndrome. This is a condition that classically presents as a increasing need for extra oxygen while also having a total whiteout of your lungs on chest x-ray. The whole thing just goes white. So the thing is, your chest x-ray kind of starts off white, And when the x-rays hit it, it becomes black, right? So bones will stop the flow of those x-rays. And so when you see bones on an x-ray, they show up white because nothing has changed and the x-rays didn't get through, right? So with COVID, instead of seeing this, relatively light black area in your lungs, because the lungs are just soft tissue, they don't stop x-rays. So when it becomes white, you've got a bunch of stuff in there, right? With ARDS, there's a whole bunch of inflammation, and then fluid gets in there. We call it non-cardiogenic pulmonary edema. So this is fluid in the lungs that does not come from your heart failing. That's a very common reason for fluid to get into your lungs. If your heart is not doing so well and things back up. But in this case, it's just from a bunch of inflammation. Now, as you can imagine, when the chest x-ray gets whited out, that is really bad. And we do see these high oxygen requirements, which makes it really look like ARDS. And yet, this is not quite the case. This is not quite what's happening. It seems that when we do the typical ARDS treatment pathway, what do we do for that? We have some studies that found that people with this condition tend to do better if you give them smaller volumes. Their breath needs to be smaller compared to their body weight. And then we also are very careful about how much pressure we use in their lungs. Because people with ARDS lungs typically have very stiff lungs. You have to use a lot of pressure to get them to inflate right. What's interesting about this picture in COVID-19 is that it doesn't behave the same way. It doesn't quite look like that. Their lungs are actually weirdly compliant. You can actually move them with less pressure. They've done some autopsies on people who have COVID-19 who died, and it looks like their lungs are filled with hyaluronic acid. Hyaluronic acid is kind of a molecule, a GAG or glycosaminoglycan, that is it acts like a lubrication for wherever it is. You find it in a lot of kind of structural tissues and stuff like the cartilage, where it kind of keeps everything kind of flowing and compliant and stuff like that. But if you get a whole bunch of hyaluronic acid just kind of secreted everywhere in your lungs, it's going to make it really hard for oxygen to get across into the blood. It more or less just acts as a wall that prevents diffusion. That may be what we're seeing with this COVID-19 ARDS as opposed to real ARDS, which this does not seem to be. The viral pneumonia of COVID has two kind of danger zones as we currently think about them. And keep in mind that all of this could change once we kind of, know more about this. But what we're seeing is, there's a danger zone around day 7 and a danger zone around day 14, roughly speaking. So these days can be a little different from person to person as far as when they'll decompensate. But those kind of ranges are what we're looking for when we're thinking, okay, can we send this guy home? Do we have to keep him? Is there a risk that he's going to deteriorate a lot when we send him home? Because we don't want that. And so if you're doing pretty well on day 15, we're generally less worried about you. Of course, there are other factors to think about, including age, comorbidity, race, the presence of gastrointestinal manifestations, which once again, 40-50+% of cases, and they tend to do a bit worse. Why is that, by the way? Why is it that some people get COVID and don't feel a thing, and others get severely ill? One possibility is that mortality may be related more to your immune system's response to the virus than the virus itself. You see, your immune system's main function is to distinguish self from non-self. Once it does that, it will then proceed to go ahead and destroy all the non-self. It needs to do this in an orderly manner that is also efficient. Too timid a response won't get the job done, but a too zealous response is going to damage everything around the offending process. When we talk about the immune response to coronavirus being excessive or inappropriate, we talk about something called cytokine storm, a kind of broad umbrella term for when the immune system goes into overdrive and just unloads its whole arsenal indiscriminately around a whole area, so to speak. More on that in the primer on my blog in the description. By the end of this, I imagine we'll have a better idea of patient-specific factors that might be able to predict an individual's risk for decompensation. One thing to remember, the fact that the fatality rate is something like 0.4% or whatever it ends up being once all this is said or done, does not mean that only 0.4% end up getting so sick that they need medical attention or sick enough to require hospitalization or the ICU. With adequate medical support, we can keep the mortality rate that low. Once the healthcare system becomes overwhelmed, we start having to, ration and reuse. And what we'll inevitably see at that point is a rising mortality rate. There's a mortality rate that comes with the natural history of disease. And that's what COVID-19 looks like in the wild. And there's a mortality rate that comes with COVID-19 in the context of modern medicine. I can tell you for a fact that there's plenty of people who are alive only but for the resources it took to keep their lungs physically moving, whether that be a ventilator or a BiPAP machine or something like that. And I've had to unilaterally DNR a 33-year-old. The picture gets grisly real fast when the system runs out of resources. The mortality rate didn't get that low by itself. Never forget that. An interesting aspect of this disease is how very hypercoagulable it makes people. This often puts you at high risk of forming clots, especially in your legs, which have a risk of breaking away and then shooting up to your lungs. This is what's called a pulmonary embolism. We've been seeing a great number of these in the hospitals, and we actually even started putting people on blood thinners for this very regularly, which is super irregular. I mean, none of us have anticoagulated people for a viral pneumonia before. It's just not a thing. And this clot-forming tendency may represent a major driver of morbidity, too, as it's been implicated in the acute effects of COVID, like renal failure, liver damage. So, there's that. What a time to be alive. A pulmonary embolism is almost like a heart attack, except it's really more like a lung attack. It's just the same thing, but more in your lungs. One last thing I thought was interesting about the manifestations of the disease is the concept that the severity of COVID-19 may vary depending on your blood type. I remember the first time I heard a doctor on TV asked about this, and I shared the baffled look on her face like, what? Is that even a consideration? Of course that's not a significant factor. This is definitely one of those aspects that flew a little under the radar at first. It's really only getting larger studies now. We have a few observational studies and a Wuhan study already, but most recently we have some preliminary data from the popular genetic testing company 23andMe, showcasing a large observational study they carried out via their testing services. And this seems to align with the results of what other studies are finding. By the way, guys, links to the resources on all of this in the description. Short story. Preliminary data suggests that blood type O may make you anywhere around 10 to 20% less likely to get COVID when adjusted for sex, age, BMI, ethnicities, and comorbidities. It's also associated with a decreased need for hospitalization, so decreased severity of the disease as well. This apparently held true as well when they factored in exposure data, although it seems this may have been collected merely in the form of occupational data. More to come on this one, although honestly I'm not sure how much this will actually affect the situation. It seems more like an interesting little quirk, but you'd never know. It's kind of like the concept right now that men get hit harder and perhaps bald men get hit even harder. Who knows how relevant these factors will end up being? It may factor into our risk stratification models for wave 2. It may not. We may find out that because they didn't control for age in some of the studies where they were able to look at bald men's data, the association may not really exist. I want to stress again that so much of this may turn out to be spurious data. Science is a process, and we have to understand that when you barrel headlong into an area of study the way we are with coronaviruses, there's going to be some bumps on the road. It's going to be that way. Ooh, oh no. Here comes the fun one. What can we do about this? There's a lot of bad news here. Surely modern medicine can come up with something of use against this plague. Well, maybe. So, if you remember what we were talking about earlier with the cytokine storms and how our own immune systems may be at fault for some of the more lethal instances of COVID, a variety of treatments have been directed at modulating the function of the immune system in a way that might make you less likely to have an exaggerated immune response. For instance, one thing we regularly do these days for patients requiring oxygen who are positive for COVID is give them corticosteroids. These have been a mainstay during the SARS epidemic and were associated with a variety of improved outcomes, including reduced fever, reduced radiographic infiltrates, and improved oxygen requirements, with some studies showing decreased mortality and hospital stays. But then again, some of these were associated with heavier SARS viral load and may arguably have aggravated the disease in some cases. We're basically making that shit up as we go, if I'm being totally honest. I will say that while making this video, the recovery trial released some preprint stuff that suggests a mortality benefit, but to be clear, this has not been formally published yet, and it hasn't been fully peer-reviewed yet at the time of the making of this video. So it's not final, but it is some promising, interesting stuff on dexamethasone. We're going to have to do some more studies to see that, but given how marked that finding is, I think a lot of people are kind of somewhat convinced by that. And honestly, we've been kind of doing that anyway, not specifically with dexamethasone, but with solumedrol. A lot of these steroids are actually pretty similar. Everybody seems to think that early intervention is really what might help as far as this whole cytokine storm. The idea is that once the damage has already been done, it's a little bit late, I guess. Once you do the corticosteroids, once the cytokines have already been produced and released, the idea is that probably they would be less effective. Part of the reason that people are really opting towards more early intervention is because that's kind of how SARS and MERS, we typically really only were able to do anything to them with early intervention. Then, of course, there's the whole issue of chloroquine and hydroxychloroquine. Part of the rationale is that these drugs tend to have an immunomodulating effect, for instance, tamping down cytokines like IL-6, and may help to combat any cytokine storm. Let's get a few things out of the way right off the bat. It's true that we do have quite a bit of data for these drugs, as they've been around for a while. They've mainly been used to treat malaria and rheumatologic illnesses like lupus. That does not mean we necessarily know it's safe or effective for people with COVID-19. In patients with lupus or malaria, the risk-benefit profile tends to be more clearly skewed towards taking the drug. In people with COVID, that's not necessarily clear yet. And in what cases exactly? I mean, what if you have mild COVID? Is it worth it then? Going on from that, if it's clear that some patients don't have a favorable risk-benefit ratio, then where do we draw the line? We have to have a good idea of what the benefits are before we can draw that line. And that's what a series of studies are trying to do right now. Initial studies suggested that these drugs, with or without a macrolide, like azithromycin, which by itself has had some broad anti-inflammatory effects, may alleviate symptoms and perhaps delay disease progression. The original study for azithro and hydroxychloroquine focused on viral shedding at day 6, by the way. Nothing about morbidity or mortality. The chloroquines are thought to help with coronaviruses by inhibiting receptor recognition, inhibiting membrane fusion by acidifying vesicles, inhibiting T-cell activation, and reducing cytokine production. A Brazilian phase 2b clinical trial showed significantly increased cardiovascular mortality with chloroquine in COVID. Multiple studies have shown that hydroxychloroquine doesn't seem to make any difference for COVID patients hospitalized requiring oxygen. There are some studies that showed some symptomatic improvement in milder cases, but there's a great many drawbacks to just about all of these so far, as of July 2020. A fairly large observational study out of New York found no mortality or ICU/ventilator use difference in patients given hydroxychloroquine. A study-by-study look at this is a little beyond the scope of this video, but I'll link a nice review article in the description for those of you who are interested to know more. Suffice it to say that the current evidence does not clearly show us that hydroxychloroquine or chloroquine are effective for COVID. Note, by the way, that the therapeutic index for chloroquine is like 3. So the 3 times the dose that it takes to start having an effect is the dose that it starts to have a toxic effect, which is not a very forgiving range. Until there's some clear evidence of benefits specifically for COVID-19, I'd be cautious about the use of hydroxychloroquine. At the moment, our institution doesn't really use it anymore. We used to. We actually used to use the hydroxychloroquine and azithromycin combination. We strictly do not know if it has any benefit in prophylaxis, and the evidence for its use in treatment are pretty conflicting. The combination of hydroxychloroquine and macrolide is definitely off the table at this point, as we found the unacceptable cardiovascular mortality. And, the FDA at this point has revoked that compassionate use kind of approval that it previously had for hydroxychloroquine. Anecdotally, I can tell you that in the hospital, we noticed these differences. So back when we were using, for instance, hydroxychloroquine and azithromycin, we were shocking people more, which is weird. Because when you have a code blue, somebody dies, you go and you try and resuscitate them, CPR, the whole deal, ACLS. And you really only shock people for ventricular tachycardia or ventricular fibrillation, VTAC, VFib. And that's relatively rare. It happens, but it doesn't happen that often. And in those months when we were giving that combination or just the hydroxychloroquine, you noticed more shocks during these codes. You just noticed them. You may not have seen the torsade de pointe or, the other long QT beforehand. You may not have captured that, but you're seeing a lot of shocks. And that just didn't seem like a coincidence to me. For the moment, we do have a Canadian randomized controlled trial on post-exposure prophylaxis. That is, medication to prevent infection that's taken after you've already been exposed to the virus. And this suggests that in this context, hydroxychloroquine does not appear to prevent infection in moderate and high-risk exposures. In this case, risk is being defined as confirmed COVID-19 at a distance of less than 6 feet or more than 10 minutes while wearing neither a face mask or a eye shield. That's high-risk exposure. And while wearing a face mask and no eye shield is moderate risk exposure. Remdesivir is another therapeutic agent that's got a lot of attention lately. It's an RNA polymerase inhibitor that's meant to interfere with COVID's ability to replicate. Remember, it's an RNA virus, so in order to make more of itself, it needs an RNA polymerase. For the chemistry peeps out there, it is a single diastereomer monophosphoramidate prodrug designed for the intracellular delivery of a modified adenine nucleoside analog. It is not a suicide inactivator either, which is kind of what I thought it would be in the beginning. The intracellular active version of the drug is actually triphosphorylated and therefore can be incorporated into a growing RNA chain. Really what happens is that it is a delayed chain terminator. With the next nucleotide coming along, it sterically clashes with the growing RNA chain about 4 positions down from where it's inserted. And so, in other words, it fits into the polymerase and everything functions as normal until a little while later when all of a sudden the old growing RNA molecule becomes kind of kinked, and that kind of stops the growth of the thing entirely. And so it can't make more RNA of itself. That's the idea. It can't make more of itself if you stop it from making more of that RNA. So how does it actually work? After all, it was developed for Ebola and hepatitis C with the same theoretical basis, and it didn't really help. Well, the first double-blinded randomized control trial, which is out of Wuhan, that we have on the subject, has a subject number N equals 236, and it looked at an intention to treat and per protocol analysis. They found no difference in time to recovery within 28 days in either analysis. Now, they actually had found that while it was not statistically powered to have been able to find that difference, simply because China was so successful at decreasing their viral, prevalence, the statistical analysis suggests that even if they were better powered, they would still not have been able to demonstrate a difference. However, despite this being the most technically sophisticated type of randomized control trial, people are not really convinced, and there's actually a follow-up trial that is underway. The ACTT trial in the U.S. Has an N equals 1,063 and demonstrate 31% faster time to recovery, importantly with no mortality benefit. This was put out by the National Institute of Allergy and Infectious Disease and generated a bit of buzz at the time. Note that if you were going to die of COVID, this study says that it isn't going to really change that. Remarkably, Gilead, the company that makes remdesivir, came out with a simple trial on the same day that more or less found that their own drug doesn't really do much for COVID. time to recovery and all, at least in severe cases. And then now they're doing follow-ups for more mild and moderate cases. At the moment, we have no data on pre-exposure prophylaxis. In other words, we're just going to have to see what happens if you just take daily medication in case you get exposed. One last therapeutic option that we're going to go into here before we start talking more deeply about public health measures is convalescent plasma. The idea behind this is that people who get COVID and recover from it, convalescent means recovering from an illness, have neutralizing antibodies against coronavirus spike proteins. The idea behind this is that people who get COVID and recover from it, convalescent means recovering from a disease, have neutralizing antibodies against the coronavirus spike proteins, proteins that are crucial for the virus to enter a cell. And these antibodies, like all other antibodies, reside in the blood plasma, the clear part without the blood cells in it if you were to centrifuge a sample of blood. If we were to take these antibodies and give them to somebody who doesn't have them, we can give them something called passive immunity, a way of helping their immune system fight the virus without necessarily giving their immune system its own weapons to do so. Remember that these are given exogenously, so your body isn't making them. The hope is that these infusions of antibody plasma will help you cope with the virus until your own immune system develops its own neutralizing antibodies to kind of take over and start doing things on its own. This strategy has been tested in other similar respiratory illnesses, namely SARS, and have shown some promising results. Now, specifically for COVID-19, the data here is pretty sparse. We have some small, non-randomized controlled trials, and we're talking often 10 patients or less for the most part. And I'm loath to draw any conclusions based on that. Larger, more sophisticated trials for convalescent plasma are ongoing. You may have heard of any number of other agents currently being tested for COVID. Famotidine, tocilizumab, lopinavir, ritonavir, and many others. I'm not going to get too far into the weeds on those. If a lot of the data on these other major players is preliminary, the data on each of these is severely anemic at best. Of course, any of these could shoot to prominence in the future, so therapeutics is definitely a space to keep an eye on for the next few months to years. For those of you who really want an extensive list of potential interventions, check out Potential Interventions for Novel Coronavirus in China, a Systematic Review by Zhang et al., link in the description. Then there's the issue of things like vitamins. At my institution, I can tell you it's not uncommon to see patients on regular doses of things like multivitamins, B6, vitamin C, vitamin D, and zinc. These are just kind of a broad nutritional support in case of any occult deficiencies a person might have lying around that may leave them with a less than optimal immune system. Vitamin D specifically has been linked in multiple studies, links in the description, suggesting, not proving, that it may have an effect on the course of COVID. And something that came as a surprise to me is that it makes sense mechanistically. Vitamin D has been found to tip the balance of pro- and anti-inflammatory cytokines toward the anti-inflammatory end of the spectrum. Vitamin A has been shown to decrease complications of HIV, measles, and malaria, and some have suggested its use in COVID. Intravenous vitamin C is being researched as a potential treatment to support patients going into ARDS, and mechanistic in vitro studies have suggested that high doses of vitamin C can have a virus-killing effect, especially in the presence of copper or iron. Now, that last part about the copper and the iron, I wouldn't put necessarily a whole lot of stock into that, as that sounds like the type of thing that will end up being in vitro only. On top of that, things like B6 and zinc have a mild, broad anti-inflammatory effect that may or may not be of use. I've tried it before personally on some of my patients. Questionable benefit. These are honestly used because it couldn't possibly hurt. Too much zinc can cause copper deficiency. But, aside from that, at least theoretically, it should help them. And these are dirt cheap, so, it's not going to cost them a whole lot if we give it to them. If we're going to use hydroxychloroquine from time to time, we might as well throw in some vitamins, right? Let's switch gears for a moment and talk about something called R0. R0 is what's called the basic reproduction number in epidemiology. It's a dynamic number that shows how many cases one would expect to arise from every one confirmed case in a population where all individuals are susceptible to infection. In other words, if you have one confirmed case in the population, under the circumstances around that case at the time, how many people would we expect to become infected as a result of that one person's presence? Technically, it refers to the spread in a population where nobody else is immune. So as the pandemic rages longer and longer, the number becomes a bit more of a distortion. The higher the R naught value, the harder it is to control an infection. And since it's a ratio, a number greater than 1 denotes that each case is going to spread to more than one person, and the numbers of overall cases are going to go up. Whereas a number less than 1 denotes that the virus is kind of going away on its own. Another interesting application of this parameter is an estimation of how many people will still be susceptible in what's called endemic equilibrium, the state where a disease has become common and entrenched or endemic to a region, and a slower trickle of new cases is essentially expected to come in indefinitely at a certain equilibrium with the rate of cases that are resolving. The equilibrium is typically 1 over R naught. R naught is, as I mentioned, a dynamic number, and a value for one outbreak for a given disease is likely not going to apply to a different outbreak in a different region with different people and their specific behaviors. It's affected by people's behaviors, so this won't tell us much about how effective a vaccination campaign will be. In general, things like airborne infections are going to have much higher R naughts, the highest R naughts, and fecal oral spreaders will have the lowest Rs. One last nuance that we're not going to delve too far into here is the fact that, so remember, R naught will become a distortion as things move away from the ideal case that it applies to. There's something different called the effective reproduction number that then becomes what we're really calculating when we look at reproduction number. What is it effectively right now, as opposed to what's the basic thing that we would calculate. So why am I even talking about this? It sounds like a bunch of abstract math stuff. How does it apply in real life? Because the public health measures that you see being implemented around you are primarily interventions aimed at lowering R naught. Measures like social distancing, hand sanitizing, mask wearing, stop touching my face, goddamn, and shutting down large gatherings are all meant to reduce R naught so that the curve of total active infections flattens. This is important because, as I mentioned earlier, if the number of active cases overwhelms the healthcare system, you're going to see a rise in mortality. So that's what you do to prevent the spread, but surely these measures can't stay on like this forever, right? The economic impact alone would be astronomical. Now, there's a couple elements to unpack there. On the one hand, it's a decent point to say that we don't have a lot of guidance regarding when exactly we can open back up. Two potential endpoints here are the introduction of a vaccine and the achievement of herd immunity, both of which we'll touch on in more detail in a minute. But let me spend a second on that second sentence there just a second ago, as you may have rolled your eyes at that part about the money. And to be honest, I rolled my eyes at that part to begin with too. But I think there's actually an argument to be made there. If people can't pay for their rent or food or what have you, there's going to be consequences to that. There's probably going to be deaths as a consequence to that. If people are scared to come in and get medical care, there's going to be consequences to that. The stress that COVID places on the healthcare system may cause patients with other severe illnesses to delay or forego essential medical care, and people will die as a result. People will die from the coronavirus, and people will die as a result of complete shutdown. The thing is that the COVID deaths are right in front of us, and we can count them right now, whereas the morbidity and mortality attributed to the shutdown itself is likely only to be measurable in the aftermath of this whole crisis. As far as I can tell, there will be deaths both ways. It's just a matter of how many each way. The worst case scenario for COVID was supposed to be something like 2.26 million in the US originally. And then they downgraded that to 100 to 200,000. And we'll likely see that target move as time passes. I mean, right now, we're already kind of moving past these targets. So how many deaths might happen as a result of the shutdown? Well, that's unclear. Super unclear. Let me stress to you that what we're seeing right now is utterly unprecedented. Some of you may feel frustrated with your governors and public officials about the lockdowns or other rules that you disagree with. Remember, this thing is so new that literally nobody is an expert. And we're all making some educated guesses here and hedged bets. If you feel an overwhelming conviction that your way of doing things is the best, I would urge you to re-examine the strength of your evidence. The more I look at the literature, the more I feel justified in waiting longer before I say anything for certain. Nobody should feel certain that their way is the best at this point. Your conviction may be right or wrong once things pan out, but remember that now your guess, like everyone else's, is exactly that, a guess. This video simply seeks to make your guess a better educated one. So, first let's talk about the concept of herd immunity. This is the idea that the presence of enough immune or immunized individuals within a susceptible population will eventually be enough to retard the spread of disease. Now, the big questions here are, how much of a population need to be immune before we have herd immunity? Diseases each have their own thresholds for herd immunity. R naught factors in here, as the typical threshold is going to be 1 minus the quantity 1 over R naught. The big takeaway from that, what does that relationship mean? Well, a smaller R naught will generally mean that fewer people need to be immune to get the herd effect. That's huge. Let me say that one more time. A smaller R naught will generally mean that fewer people need to be immune to get the herd effect. Okay? Pandemic H1N1 influenza had an R naught of about 1.6-ish, and the herd threshold was about 40%. But measles had an R naught of 12 to 18 and required 83 to 94% threshold before herd effect kicked in. There's a few things we should know about herd immunity. One is that it's not necessarily permanent or static. Herd immunity exerts evolutionary and selection pressure on microbes and their antigens, thereby potentially leading to serotype replacement, a process by which a virus can change enough that entirely new antibodies are needed for immunity. It can also be affected by the duration of immunity conferred by a given agent. So, for instance, it would be hard or impossible to achieve herd immunity in an infection that only gives you a few weeks of herd immunity. At the moment, we aren't really sure how long people will have immunity for SARS-CoV. So we'll see. Honestly, a lot of the stuff that I'm seeing as far as like studies and even my own experience, I'm really leaning towards the idea that SARS-CoV-2 likely only gives you weeks to months of immunity. It may wear off pretty quickly. So short story, if you're gung-ho about trying to get herd immunity, the safest way of doing that and the fastest way of achieving herd immunity is actually by keeping these measures in place to lower R naught while we wait to achieve an endemic equilibrium, which I'm pretty sure is going to happen at this point. It's going to be endemic to every single continent, I believe. And now you've seen the math behind why. If R naught rises too much, pretty much everybody will have to get infected before the herd effect kicks in. And at that point, a lot of people will have died. Now we come to vaccinations, the big wild card in the mix. If we get an effective vaccine tomorrow, everything I just talked about will be largely irrelevant. We've heard all manner of estimates about when this might come out, ranging from the end of this year, 2020, to early to late 2021. All we can really say about that right now is that we should be able to develop a vaccine at some point, unless we get that whole serotype conversion, issue, and then we might have to get yearly vaccines like seasonal influenza. We feel reasonably certain that this kind of thing generally is doable with COVID-19, with mammalian antibodies, from animal studies that do seem to show immunity. The mammalian antibodies that we produce should also confer immunity. But also remember that for viruses like hepatitis C and HIV, we may form antibodies, but they don't necessarily mean that we're immune to those diseases. There's a bunch of vaccines in development right now, and some of those are even in early phase 3 trials, like the one being developed by Moderna that just finalized its protocol. The previous record for how quickly we can make a new vaccine was something like 4 years. I would imagine moving this quickly means plenty of vaccine candidates under development today will likely fall through. Under normal circumstances, that's actually how this goes. Most drugs that make it all the way to clinical trials don't end up making it commercially. The common wisdom that we've been given is something like 12 to 18 months since the start of the outbreak, but honestly, who knows? I would imagine that it'll actually be longer than that, but I'd love my pessimism to be proven wrong. The point here is that an effective vaccine would be the big gun. It would potentially be a game ender, if not a total game changer. Now, vaccine versus herd immunity seems to be the dichotomy I'm kind of seeing in the collective conscience, at least here in America. I'd like to also mention the importance of testing here, because it's really a fundamental thing that could make a huge difference with regard to lockdown. Remember I said South Korea and China had recently been hit hard by viruses like SARS and MERS, and therefore were more prepared to respond? Well, China is a bit of a special case with all the nonsense we're finding out about their virus response. So we won't linger on them too much. Suffice to say that their draconian lockdowns will work if you happen to be a communist authoritarian nation like China, and you can do whatever the hell you want. But South Korea is a really interesting case. They knew from the get-go exactly what to do, and they were ramping up testing and contact tracing capacity, and they knew that that was crucial to stopping the spread of the virus. Within 2 weeks of their first case, they were making 100,000 test kits per day. They literally have drive-through testing there. Another aspect of this is contact tracing. Now, the Korean government has some advantages there as far as being able to use CCTV and financial records a bit more liberally than the US can. But ultimately, the concept is the same. There's no need for mass lockdowns if we can tell with individual level accuracy who's been exposed. Instead, you could do individual quarantines, which would dramatically minimize the economic impact and the more widespread quarantines would then have. Of course, these strategies are most manageable when they are implemented as early as possible. Otherwise, you're just playing catch-up. There's a bit more basics on vaccination types and diagnostic modalities in the primary, if you're more curious about that. COVID-19 and its associated recession, more on that in an upcoming video, is going to be remembered as one of, if not the defining struggle of our generation. Unless the supervolcano in Yellowstone, which is due to blow any day now, gets us, then that will be it. But as it stands, this is probably going to be one of the history-defining moments that we've lived through. And I'll tell you, man, I have had enough of making history. This whole history nonsense is bullshit. I don't want any more of this. Normal would be nice right about now. A few take-home points before we go. Physical distancing and mask wearing are important because they reduce the basic reproduction number. This, in turn, is a big part of achieving herd immunity, and that's related to the basic reproduction number, or R naught. We have some drugs in the pipeline that may help, none of which have demonstrated mortality benefit, except maybe steroids like dexamethasone. I.e., they won't save your life if you're going to die, but they may speed your recovery symptomatically. And even the study on dexamethasone, a corticosteroid like many others, was somewhat weak evidence. It was just somewhat dramatic, is really all it was. We have no drugs that have proven post or pre-exposure prophylaxis value, including chloroquine and hydroxychloroquine at the moment. Sorry, but at the moment we don't know enough to say that chloroquine and hydroxychloroquine are safe and effective for COVID-19. Based on where the literature seems to be going, I'm not too hopeful for either of those. There's that new Henry Ford retrospective study. I'll comment it on not Lern, my other YouTube channel, just because I already shot most of this video before this thing came out with the whole Henry Ford study. I'm somewhat well acquainted with it. Look, quick takeaway points before I'll mention it again on not Lern. So this is a retrospective study. It's done in a single place. So these are 5 institutions in just Detroit, Michigan. So it's just what they recruited in that area. It is not randomized. It is not blinded. So there's a lot of things about this study that are just not optimal. They're just not optimal. And then, you see this dramatic kind of effect with chloroquine and hydroxychloroquine that goes against a lot of the rest of the literature. And then you go to the financials of that study. And then all of a sudden you see that it's funded by Bayer and Gilead. And it's like, oh, well, that's fun. Bayer and Gilead funded that. Great. I wouldn't make a whole lot of fuss over that study, honestly. It's just one study. Look at the body of literature. That's what I would advise you to do. The vaccine may be a big game changer, but we may not get that for quite some time. We don't necessarily know what to do in the meantime. We don't have a solid idea of when we can reopen from our lockdowns. But we do know that as of now, nothing has changed. COVID hasn't gone anywhere. And we don't have a vaccine or herd immunity yet. Importantly, we don't know how this situation will shift once flu season comes around, and we're dealing with both at once. Co-infection and secondary bacterial infections are going to be far more relevant during flu season. If you look at the CDC's 2018 to 2019 flu season mortality estimates, you'll see that roughly 34,000 people died of the flu in the USA during that season. But remember, influenza itself only kills really the immunocompromised. Most people actually die of complications of influenza, especially secondary bacterial pneumonia, which is not uncommonly caused by Staphylococcus aureus. Our co-infection rate during the initial wave wasn't so high that we actually really even searched too hard for co-infection. It was supposed to be like less than 1%, a waste of resources to really regularly influenza swab everybody. However, once we're into full-blown influenza season, who knows what COVID plus flu is going to equal. That could be a massacre in just waiting to happen. As frustrating as the breakneck pace of discovery and changing of guidelines can be, we have to remember that science is a process. There will be mistakes in the coming months, and the prevailing wisdom on various things will change. These are not an indictment of science, but rather a reflection of individual authors and institutions, like in the case of that recently retracted Lancet article, and the fact that discovery is often more of a wobbly children's stick figure than a straight line. As we ride this roller coaster that we've all been forced into, let's all try to remember that we're truly all in this together. We're all going through this at once. I have never felt more like a citizen of the world as during this particular crisis. It's like we all have something huge in common, regardless of where we live or what we do. And I only hope that once this is all over, and it will be over eventually, that we won't lose that sense of oneness. Well, that's about it then, guys. Thanks for watching. If you liked the video, please don't forget to drop a like. And if you'd like to see more videos like this, go ahead and hit that subscribe button and turn the notifications on by hitting that bell button. I may make a channel trailer to this effect at some point, but basically, I want to use this channel to answer a question that some people have periodically asked me from time to time, and that's, how do you know about so many different things? I tend to have something to say about politics, finance, history, science, whatever we end up talking about at the time. For me personally, this is because I enjoy learning a lot of different things, but also because I insist on satisfying my curiosity. Basically. So whenever I have a question, even a minor one that pops into my head, I just take up my phone and I Google it. In the modern day, we have basically the sum total of all, well, not exactly, but almost the sum total of all human knowledge in the palm of our hands 24/7. I just feel like, if you have that, you should use it, So you'd be surprised how much you can discover just by not letting those stray questions escape you. This channel is kind of my attempt to bring you my stray thoughts in a more organized way, and to encourage you to try and maybe make a similar habit, see if that might help. And finally, a mention for my other channel, Not Learn, where I'm a bit less formal and a bit more overtly opinionated. This has been Ronald, and you just got learned.